So next up, we have Rob Adams, and I want to start off with a reminder that the views expressed by our speakers today are their own views, and they're not representative of the organizations that they are a part of. So our next speaker, Dr. Rob Adams, is an advanced propulsion technologist at NASA. Throughout his 20-year career at NASA, Dr. Adams has led several high-profile projects and studies with a number of NASA centers, government organizations, industry groups, and also academia. Dr. Adams holds multiple master's degrees in mechanical engineering, aerospace engineering, nuclear engineering, and then a PhD in mechanical engineering from University of Alabama in Huntsville. Dr. Adams is the founder and CEO of Paradis Systems, which develops mobile spacecraft simulators for fun and for education. Please welcome Dr. Rob Adams. And so I see the slides up, and then I see you and I hear you. Beautiful. So
okay, great.
I'll let you go away.
Okay, so I actually have two different talks that I'm going to give in the next 45 minutes. So I'll do one, answer questions, and then we can, if we have time, go into the other one. The first thing that Michael asked me to talk about is the Pulsed Fission Fusion concept. Let me see if I can make this a little more palatable. There we go. Pulsed Fission Fusion is a propulsion system that we've been working on at Marshall Space Flight Center since about 2012, and has a great deal of applications for the future infrastructure of space. So first, let me, there we go. There we go. Okay, so without me messing with it, this is a magnetic nozzle. What you see being injected are shells of liquid lithium, both as a cone and a cylinder, and then you see a tiny little target in between those two. This target right here is uranium 235, 238, and some fusion fuels, which could be generally deuterium and tritium, but we could look at other fusion fuels like DD or DH3, helium-3, or whatnot. We run a high pulsed current through the lithium to compress this target by an order of magnitude, compressing what was once something the size of a horse pill into something much smaller, where it goes supercritical and explodes, vaporizing and turning into plasma both the target and the injected lithium. That lithium, that entire plasma expands out as a ball, as you can see here, until it interacts with the magnetic fields from the magnetic nozzle, which pushes the plasma out the back, and we get thrust. We do that once a second, and we have a phenomenal new propulsion system that will take us around the solar system. Given how cranky this video is, I guess I'll close it for now. And if anyone has any questions, I can kind of launch into it again. So this slide right here is really just showing what we saw in the video there. So that's what we're talking about with Pulsed Fission Fusion. Our goal is to design the system in such a way that you could have an entire propulsive nacelle that could fit onto the upper stage of a Block 2 SLS, Space Launch System, or potentially a Starship. Then you could attach any payload you wanted to and propel wherever you wanted to go. Right now, we're looking at two different options. One is looking at a pure fission concept that uses a more traditional pressure plate nozzle. So that's a solid nozzle, if you will. And that's shown over on the left. And we're imagining that for Earth-Moon operations and early use in interplanetary exploration. On the right would be the magnetic nozzle using both fission and fusion, and then that would be solar system operations. So if you can see this kind of dark chart here, this is the trajectory for flying from the Earth to Mars. And so just to get you oriented, the sun is in the center of the figure, and then Venus's orbit shown purple, Earth is in blue, and then Mars is in red here. Now, if you look at most trajectories, they have a very elliptical look to them, especially interplanetary trajectories. the power that comes from Puff here, you notice that we're flying to Mars almost like it's a straight line. The red lines there are actually showing where the burns happen. So what would happen here is that we would start in low Earth orbit and we would light the Puff system off, and it would actually burn for about 2.5 days. We would quickly spiral out of the Earth's gravitational field, and then we would need about 30 days to fly to Mars. And then you can see the burns at Mars, where we actually have to slow down a little bit so that we can capture at Mars. So the entire trip is taking 37 days, and that's carrying a 25 metric ton payload crew compartment that would carry, 4 to 6 people over that month. Another important thing to notice about this trajectory is that where it says Earth here is actually showing where Earth would be when we arrive at Mars. So when we look at Mars trajectories, we have a lot of problems in waiting for the Earth to get back in position where we can leave Mars and come back to Earth. And so that can actually add a great deal of time to the entire mission trajectory. Here, because we're able to get there so quick, we can turn around and come back. And so now, instead of talking about 2, 3, or even longer year missions to Mars, we're talking about the potential of doing entire missions in 6 months to a year. Now, this concept's also powerful enough for us to look at near interstellar applications. And near interstellar is the term we use when we want to talk about leaving the solar system but not quite getting to another star. And so here you can see where we're doing a massive burn at Earth again, and then we spend 48 days flying inbound to the sun. And then we do a 2.5-day burn approaching the sun within about 3 solar radii. And doing the burn that close to the sun, actually allows us to whip around and achieve some extremely high velocities, such that Voyager 1, that's taken 50 years to reach the solar system termination shock, we would reach that in 5 years. And there is a very interesting part of the solar system called the solar gravitational lens, and that's at about 650 AU. That's 650 times the distance between the Earth and the sun. That is a place where if you park a telescope there, the sun's gravity focuses light onto that point. And so now you have a telescope with an aperture the size of the sun. And so there's research going on right now about actually being able to image exoplanets and look for extraterrestrial life, if we got missions out to the solar gravitational lens. Other missions could be like chasing down interstellar objects like Oumuamua that came through a couple of years ago. There was another one that came through a few months ago. Being able to look at these interstellar things, fully disprove that they're natural phenomena and not aliens coming to visit us, things like that. So the Pulsed Fission Fusion concept has a number of different subsystems. I don't want to get into too many details, except that I want to talk about the fact that in developing these different technologies, we're actually coming up with a number of spin-offs. And so this is a great reason for me to want to be here and presenting, is because we're looking for partners to develop these spin-offs. So one is injection of liquid lithium. And so over here on the left, we see the lithium tank. And then if you remember from the video, we're injecting both a cone and a shell, or a cone and a cylinder of lithium, because it's completing an electrical circuit where we create a massive electrical pulse that implodes the target. And so we've got a number of things going on, mainly analytical right now, but we are looking at our first experimental efforts to inject liquid lithium. The spin-offs here are mainly in the nuclear power industry, being able to use lithium as a coolant. So both for fission and for the nascent fusion concepts that are being developed, the ability to use lithium as a coolant is challenging because lithium is hard to handle, but at the same time, it's very promising. It's a very good heat conductor. And then let's see now, we have our target storage and injection system. So here is where we actually store all these tiny little horse pills of uranium and then also whatever fusion fuel that we're carrying there. We actually have to spend a lot of time designing it in such a way that it would not go critical until we wanted it to. So that's why we end up storing these targets in a very wide set of disks. The thing with fission fuel is you don't want it to get into something that resembles a ball or a cylinder, where the neutrons that are being naturally ejected would cause a chain reaction. And so I don't know that there's a whole lot of spin-off effects here. I would love to sit here and spend, the next 3 hours talking about all the physics of the implosion process and whatnot. But some of it is sensitive, obviously, and I don't think that's what everyone really cares about here. So, and then we've been doing a lot of development in injecting those targets, firing them down the length of the vehicle so that they are accurately located at the implosion point when we inject the lithium around it and cause the implosion. And so we've been doing a lot of development in coil guns. Now, this is related to rail guns, and so these are interesting technologies that have a lot of applications, both in the concept of using electromagnetic rail launchers for launching material off of the moon. There are concepts where you would use coil guns to intercept and deorbit orbital debris. We're working on a concept right now using a coil gun as a particular type of metal 3D printer that we're working on right now. So interesting stuff there. The plasma physics of the nozzle and how the plume comes out of the nozzle is pretty interesting. And so here are just a few of the equations that we have to conserve mass, momentum, and energy, both for the plasma and the non-plasma components of the vehicle here. And so we've developed, and this is mainly with my partners at the University of Alabama, Huntsville, working on a smooth particle hydrodynamics model that is quite impressive, that does a great deal of the plasma physics that we need on the plasma expansion. And so right now we're in the process of doing a number of different trade studies to figure out the right nozzle geometries and to actually make the nozzle survivable so that we can actually have nuclear explosions within a meter of the nozzle. I should note that we're talking about a nuclear explosion, but we're talking about a micro explosion. So the explosive yields here are 5 or 6 orders of magnitude of Hiroshima and Nagasaki. So we're talking energies on the order of a ton of TNT, not kilotons or megatons. And if we were talking about those higher levels, there's no way we could do this and actually survive a single explosion. So there's a fair amount of work on the thermal subsystem. Here again, we're looking at being able to reject a great deal of heat that's being generated by the explosion, and that we're having to design a fairly complex thermal subsystem. Here we're using a different coolant called FLiBe, fluorine, lithium, beryllium. And that again has a great deal of applications in the nuclear world, in that it too is a great coolant that can be a little difficult to handle. But working out the high level technology readiness level issues with FLiBe would pay off, especially with the new push towards small modular reactors that you see going on that's kind of the new breakthrough in terrestrial power generation. So here's where we're doing different models on the nozzle to look at our thermal mechanics, our steady state, and our time varying thermal mechanics, so that we can actually make sure that the nozzle survives the explosion. That's been a fun challenge, but we think we've got that one worked out at this point. So, and then for the magnetic nozzle, like we showed in the video, that has a number of technologies in it that we're in the process of working with others to develop it. We actually need a high temperature superconductor sitting in the center of each strut line to generate the magnetic fields that guides the plasma out of the back of the nozzle. And so, Brookhaven is probably the folks that are doing the most cutting edge research right now in superconductivity. Now, a number of the different fusion concepts for terrestrial power rely on these superconductors as well. And so there's a lot of interest both with Brookhaven, MIT, and then some folks over in Europe as well on these particular technologies. And of course, we're generating a great deal of neutrons and gammas when we do our implosion process. So we've spent a great deal of time making sure that we have a substantial neutron shield and gamma shield, so that the crew can be on the backside and not have to worry about anything. One of the interesting, ironic things about space exploration is that space is a very highly radiative environment. We're very protected both by the Van Allen belts and 100 miles of atmosphere, so that all the radiation being generated by the sun and by every other star in the universe doesn't come down to us, or not a whole lot. So it turns out that nuclear propulsion systems that can reduce the trip time are the greatest advantage for us in keeping down the dose rates on the astronauts. So we actually want to go nuclear so that they get exposed to less radiation, and that has been a substantial problem with any sort of Mars missions for the last 40 years that it's been looked at, is making sure that the excess cancer risk that the astronauts are exposed to are as low as possible. Right now, the current guideline is trying to reduce the lifetime astronaut cancer risks to about 3% above the normal. And so that puts some pretty strong constraints on what they can be exposed to on a trip. Before I get into this, there's one technology that I haven't mentioned, and it's actually a fairly critical one. It's called linear transformer drivers, and these are basically very high frequency, very high power pulse units. So imagine being able to generate pulses that are over a microsecond long, or less than a microsecond long, I should add, that generate mega amps at megavolts. And so you're talking about generating a terawatt pulse in a fraction of a second. The pressure that we put on our target is strictly a function of current. And so we want to run extremely high currents, but of course, if we try to do that for long time frames, then we consume a lot of power. Now, high pulse power systems have a lot of applications in, weapons technology, but also there's a lot of interesting applications in terms of medical and manufacturing applications. And so these LTDs have been looked at since the 90s, and there's a lot of research going on with them right now. And I think there's some good opportunities there to look at commercial applications. So we've been working on this since April 2012, and so this is kind of our timeline of funding that we've been able to receive, primarily on the small contributions from the Marshall leadership, NASA headquarters, and then our UAH partners having opportunities to apply to things that are, outside of the government control. We've actually reached the point right now where we've exhausted the amount of development that we can do at these lower funding levels, and so we have opportunities to branch into funding levels that are millions of dollars and then some, but we need to start locating more commercial partners that are developing some of these side technologies that can kind of work with us. And so that kind of brings me to my last chart. If I can, there we go. So there's several spin-offs that I've kind of alluded to. One is the 3D printing and decomposition technologies. And you saw Rob Hoyt talk about some of these same sorts of things. I'd love to catch up with him and find out how he's doing his stuff. But here's where we could use the LTDs and these high pulse rates to, one, force high temperature materials to fuse together. And there are, a huge number of applications for high temperature materials, higher efficient combustion systems, aircraft, looking at, everything that we do in space. We want these high temperature materials for just a number of different cases here. And so there's a fair amount of development that we're working on that right now. The idea of using the coil gun systems in combinations with the LTDs, so you have an LTD firing each coil along the coil gun with a very high, very efficient pulse, creates the possibility that we can generate, coil guns that are highly efficient for moving people and cargo, mainly cargo, around the inner solar system efficiently, and doing things here on the ground as well. Of course, using the PUF system as a terrestrial power source has a fair amount of applications. We're looking at the possibility of using this as not a small modular reactor, but kind of a medium modular reactor, where we're looking at hundreds of kilowatts of energy, or maybe a few megawatts, but with a footprint size that would be, say, a tenth of the size of a current power plant, nuclear or coal-fired. And so, of course, here we're generating very little waste, because we're turning the uranium into a plasma, so we can recycle the uranium. And that means that we could get 100% burn up of the uranium in our process, which would be, which would make nuclear extremely competitive and be a great option to deal with global climate change. In situ resource utilization, the idea of using these LTD pulses to create high energy pulses that would decompose particles, decompose materials like Rob Hoyt was talking about on station, decompose regolith and be able to separate them into its constituent parts so that they could be used later for 3D printing. That's a possibility. And then finally, molybdenum-99 is one of the most expensive materials on Earth. It is worth $1 billion a kilogram. It is used in medical imaging. If you, God forbid, should have cancer, as somebody very close to me just had, they use the decomposed product of moly-99, technetium-99, inject it into your body and use it as a trace element to find the cancer cells so that the surgeons can go after it, or that you can use targeted radiation on it. So at $1 billion a kilogram, it is not produced in the United States. The reactor systems that are used here in the U.S. are not capable of making those. So we actually import all of the moly-99 that comes into the United States, which is about half of the global production, from France and South Korea and a couple other places. So there has actually been a few $100 million spent by the DOE to rectify this situation and bring moly-99 production here into the United States. And there are options to use PUF to generate moly-99 here, and we could do that in a controlled pulsed manner, where we could create it as on demand and be able to ship it to the hospitals quickly. So with that, that ends my first talk. And let me see if there are any questions before I go to the second one. Well, real quick, I see one question as I bring this up. Time frame 10, 20 years. The optimum time, the next optimum time to go to Mars is 2035. And we can get into all the details of why 2035 is optimal. But yes, the goal would be to have Puff up, running, and doing the Mars mission by 2035. Now, I want to emphasize that Puff is not baseline for the Mars mission. This is, our group trying to make that argument to the larger NASA community. But, that is a achievable goal. Okay, so
but in full disclosure, right, sir, you are part of the NASA new concepts. I forget what the title is, but you're part of the Marshall Space Flight Center's
yes.
New what is that? What's that title?
Yeah, I'm at Marshall Space Flight Center. I'm in the Advanced Propulsion and Technology group.
Right. So it's not out of the realm of the possible that becomes a baseline. It's just not there yet.
That's right. I mean, we're what we call low TRL developing technology.
Sure.
Honestly, inside of NASA, there's not a lot going on in terms of lower TRL advanced propulsion. So if there's a couple things, but the field is a little barren right now, and it's a bit of a challenge to develop advanced propulsion. But like I said, we have opportunities that we can chase, but we need to find more commercial interest to kind of share a little load.
That's one of the things we're trying to ensure with this speaker set,
right,
the whole year, is to kind of put a spotlight on some interesting stuff. We've really tried to couch it between 2020 and 2035.
Right.
But you are actually the only person that we've had on our series that is talking about right at the edge of that technology. And really, the only one that we're talking about with a target towards Mars. But when you and I talked, it's like, okay, yeah, but there's applications right here, right now, down here on the ground that have value,
right,
in our the local environment of space. So.
Yeah, and the technologies, the spin-off technologies that I'm talking about won't take 15 years to develop.
Right.
I mean,
right. Exactly.
The 3D printing technology, the coil gun technology, those are, how do I put this? Those are the easy things.
They are, right.
Yeah, containing a 1 metric ton explosion a meter away from a nozzle, that's more of a challenge.
That's harder. Right.
So, okay, so
we got 14 minutes.
Okay, so I'm going to give a very abbreviated part of this. And the idea here is, well, I'm going to talk about a model for future space exploration and exploitation. You can see several people here at Marshall Space Flight Center worked on this. Joel Moser is the chief scientist for the United States Space Force. Joel gave a talk at a conference last year where he reviewed a Space Futures workshop. Some of the people here may have been on that Space Futures workshop. Joel had pulled together about 100 people from NASA, Space Force, industry, universities, and whatnot, put them all in a room and said, let's talk about the next 40 years in space. And what does the role need to be? And some of the earlier commenters or presenters have talked about how there's a lot of analogies to our maritime tradition here at the United States about ensuring free access for everybody. And so that's the goal here. What does that look like? And so the first workshop put together a lot of thoughts, came up with 8 possible futures, which are shown over here on the right. The most ideal one they called Star Trek. The worst one they called Dark Skies. And there is, some very obvious players that have made some very pointed statements about wanting to have dominance in space, and the ability to deny it to others. And so, it's the Space Force's job to make sure that doesn't happen. I found, his talk very compelling, and I went up and talked to him afterwards, and I said, well, what you need is a model. and I'm good at models, so let's talk about that. And so we sat down and started working up a set of goals to develop a program where we could basically inform the conversation. The Space Futures Workshop talked about which policies, which technologies, which infrastructure, and which missions need to happen to create, a strong presence in space. And then they would judge whether or not that strong presence in space was achieved by looking at how many people are in space, what does the space economy look like, and how much influence does everybody have in space. And so, we talked about being able to set up a program that could look at that both with humans in the loop or with a completely AI set to basically look at all the different options that are being thrown out there, run through all the permutations, and come up with recommendations that could be further discussed by the community. And so we sat down, and in preparation for the Ascend conference that was a couple months ago, I and one of my grad students pounded out a first cut at a Unity-based, the Unity game and simulation environment based program that would capture all of this. And of course, if you work at NASA, you got to have a good acronym. So the interns put their heads together and we came up with oracles, which I thought was excellent for what we were trying to do here. So there are three modes that oracles runs in. One is just data capture. Another is being able to put people in the loop and see what happens as you model things for the next 40 years. And then finally, this AI version that we're talking about. And so I want to leave time for questions. So I'm going to go through this really quickly. But here is our main interface here, where as we go from 2020 to 2060, we would see more and more infrastructure being built up, more orbits, more players coming out. In reality, we wouldn't have all the planets nice and lined up like this, but we actually really pounded out this interface as a first cut in a month. So I think we actually did pretty good for what we did. We've set it up so that we could have numerous different players, if you will. We basically representing different entities. So the Space Force would be an entity, NASA would be an entity, SpaceX, Blue Origin, the Canadians, the European Space Agency, the Chinese, yada, yada, so on and so forth. We could designate either they were human or AI, and if they were AI, then we have a number of different strategies, where it could be, hey, we want to, commercially exploit. We're going to focus on the economic. We're going to focus on the visionary, achieving those mission firsts. We're going to look at, we want to be dominant or aggressive. We actually want to prevent others from having access to space. Emerging for some of the smaller players that still, make a difference and whatnot. So these next couple of charts are really just kind of showing some zoom ins where we can kind of look at lots of different infrastructure that's going on at the same time. Eventually, what would happen is each one of these different pieces that are in the program at any point along the 2020 to 2060 timeframe would have the appropriate icon there, and we would be able to see both on the Earth and on other planets in orbit, whatnot, who has what infrastructure, where it is at any given moment, and just see who's developed what. Now, from there, I said there were three modes. One was data collection. So, the idea would be that if somebody had a new concept, a new piece of the puzzle, whether that's technology or a policy or a new capability or whatnot, that they would be able to bring it. We would plug it into the system, and then we could evaluate how, you know, useful it was compared to the other things. So here's one of our data entry screens, which is infrastructure. And here I picked as an example a solar thermal orbital transfer vehicle. So this has some relevance to one of the talks just recently, although it's got solar thermal to it. I picked that because everyone knows it, and nobody has a big dog in that fight. So, and here, you know, we're capturing what, you know, the experts think it would take to develop the first one in terms of time and money, and what capabilities it would generate, and what influence it would have on the potential outcomes, both population, economics, and influence. And so this is still very first cut, but that's what we're looking at. One thing I want to point out here is that if you look at the timeline where we're looking at how long it would take to develop this OTV, we ask for min and max values. So everything that we're getting from the experts, we want to, you know, treat them as random variables. And so the program will do Monte Carlo analysis between mins and maxes using, you know, almost certainly a uniform distribution, and allow a level of randomness into the program that we would evaluate over, you know, numerous runs when we let the AI execute. And so that the idea there is that we're trying to capture the fact that a lot of this data has a pretty big error band around it, let's face it, especially when it comes to cost and schedule. For policy, the idea here is that we can, you know, partner, you know, or entities can partner with others to develop technologies, to employ infrastructure that, you know, in producing some of those funds. So we have participating entities develop the solar thermal OTV. NASA, the Space Force is putting in funding, SpaceX, ESA, and the Canadians. And so, you know, NASA would get the first unit, the Space Force would get access to that unit, SpaceX would have access to all the technology, and they would go build a second unit that would fit, you know, probably better in their business model. And as usual, you know, the Europeans and the Canadians would, you know, help fund some of these projects in exchange for astronaut slots, like so here we've got them slotted for an eventual lunar base that's being supported by the OTV. And then again, we're tracking, you know, how that is affecting population, economy, and influence, and looking how other entities are affected. Technologies are really interested. The NASA has the 2020 technology hierarchy or architecture. It's also being adopted by the Space Force. NASA does not have vehicle defense systems, so we're kind of expecting that the Space Force is going to expand that technology taxonomy at some point. So, but the idea here is all of these other tabs here come right out of the taxonomy, and we break things into, I think it's 17 different categories, from propulsion to, you know, air traffic management and other things like that. And then there are categories and subcategories. And so if somebody wants to introduce a new technology, say somebody comes up with a new way to do solar thermal, or, you know, my puff concept or something like that, then we would develop a technology trade tree, which is shown here, where we go through the different technology readiness levels. Hopefully everyone's familiar with that, but that's how we grade how far along a technology's been developed. TRL1 is basically, here's a drawing on a napkin, and TRL9 is, here it is operating in space, and it's been operating in space for a couple of years now. And so between this 3D plot is showing the technology readiness levels versus the complexity of the system, whether it's a component like a valve all the way up to a complete system like a propulsion system or a thermal system. And then the third line is category. So, you know, there are different types of solar thermal systems, and here we're showing an indirect and a direct drive and an advanced indirect drive. And so each one of these blocks can influence the others, and you would find your path through all of these blocks to get to a TRL9 sort of system. And clicking on each one of those blocks would show how much we think it would take to develop that technology, who would be the best players to do that, and where are the best facilities to do that development. And so here again, we're capturing all of this information that can be used both in the simulation, but both to inform the discussions when people are in the room trying to decide what to do next. This interface allows us to kind of look at everything from different slides and shots and whatnot. So, you know, we can turn the 3D plot into 2D plots basically when we want to. When someone in a user, a player is actually in the game making decisions for their entity and whatnot, now they can start making decisions. So I'm leaving the data entry part, and now I'm talking about the people in the loop decision-making process, where we're wargaming, if you will, or simulating the next 40 years. You know, here is a interface where you're making decisions on, you know, what's the next piece of infrastructure that you want to develop, and how is it going to affect the next things that you want to do. This architecture slide is pretty slow. It's pretty, what's the word I'm looking for? Unpolished. But this format is something that NASA uses a great deal. If you imagine something like the Human Launch System, the HLS, there would be, or there are, charts that show multiple NASA and SpaceX launches assembling a particular lunar lander system, either in LEO or at the near rectilinear halo orbit that we're talking about setting up the lunar gateway at. And that at the lunar gateway, you would actually have parts of that vehicle departing and going down to low lunar orbit. And then from there, you would have the lander, you know, break apart again and land on the moon. And then you would have the ascent vehicle come back up and dock to the service module or whatever is waiting was left in low lunar orbit. And then that would bring you back to NRHO. And then that, of course, would be your departure point to get your people back to Earth again. So you can imagine that these architecture slides can get pretty complicated. And so here is where we're envisioning, you know, a more complicated version of this, allowing the people to set up particular missions that they want to execute, like getting people to and from the moon, or going and visiting an asteroid, or going to Mars, or doing something in the exploration regime. Policy is one that we're still kind of rubbing our hands about. We feel like it has to be addressed. I mean, if you look at U.S. policy as it promotes infrastructure and exploration, you cannot divorce the two. I mean, when you think about how the canals or their intercontinental railroad was built, you know, the government was a huge part of that. And of course, you know, the technologies that we're talking about using today to exploit space have been, you know, a product of a great deal of government investment as well. But, you know, especially as a government civil servant, I'm can't go to the legislative branch and say, hey, you should, you know, implement X policy and whatnot. However, right now, what we expect to do in the game is to look at what policies have been presented and pitched by, you know, the general experts and whatnot. You know, there should be tax-free operations in space like we did with the internet. There should be you know, some sort of homesteader tax credit like we did with the West, so on and so forth. And then, you know, we model what the government looks like for that entity. So here we've represented the United States, and we look at you know, why we would think a particular legislator might go for it or against it. And of course, we're not going to track actual legislators, I don't think, here. We couldn't predict who was going to be in what position over the next 40 years anyways, but we would kind of make a set of hypothetical legislators and look at how much, you know, this policy would bring into his district and how it might align with his or her sensibilities and whatnot, and be able to predict, you know, to some extent whether or not we thought the policy would get through or not. again, that one's a bit hand wavy. Yeah, pretty much how to game your way through Congress. So I think, you know, as we're developing this and we're showing this up to folks at headquarters, and Joel is showing it to the rest of the Space Force leadership, that there will come a time where we will just go to Congress and say, you know, what are we allowed to do here? And get some input, and then we'll go do that. So at the end of every year, you know, there would be actually multiple slides. So here's one, evaluating what projects you've invested in, how far they've proceeded, what part are they in the development process. This ABCDEF is a NASA standard. Phase A is conceptual design. That's you know, us sitting down with paper and going, all right, what are we going to do? C is basically the final design before we start cutting metal, which is D. E is operations, and F is disposal. So you know, you're getting the idea of what how far your projects are along, and how far they're over or under running, and they're always overrunning, right? And forcing the people to go rebalance their budgets every year. And have to cancel projects so that they can keep the ones they really want to keep alive. So, you know, here, where we're at right now is we've built this front end, but there's no back end. We just got the first inputs of funding to start building some of the back end. And so we'll start that up here very soon. In fact, in about an hour and a half, I'll be meeting with the NASA chief architect, and we'll be talking about the possibility of you know, further funding there and whatnot. So no promises, but we'll see how that goes. So, you know, this is kind of a pitch that we've put together, and we're working this. The idea would be that once we've got it implemented over the next year, that we would like to you know, put it out there for everybody to look at least some public version of it. I can imagine, especially with the Space Force involvement, that there might be a classified part of this that would, you know, obviously not go out with everybody. But the idea is that we would start soliciting, you know, input from anybody who wanted to give input, and keep as many options in there as possible, and be able to evaluate as many different options. One thing that Michael and I talked about that we just didn't have time for in the short time that we put this together is that the Bureau of Economic Analysis, which is the federal agency that actually calculates what the U.S. gross domestic product is, has a side project right now evaluating how much of the U.S. gross domestic product comes from space. And so they're actually going to release their data that they've been working on for a year next Thursday. And so the lady that's the head of the team and I will be talking after that about integrating some of their analysis and whatnot into the economic portion of this. We're also planning on conversations with the SpaceWorks folks to be able to, you know, somehow model or at least capture the data on the wargaming aspects of this as well. And then, of course, you know, my background is building and designing infrastructure, so you know, we've got that fairly covered. So lots going on here. It's a very early project that's very, you know, just getting started and whatnot, but it's pretty exciting. And at that, I think I'll shut up and see if anyone has any questions.
Dr. Adams, that was amazing. Two just boggling projects back to back. Thank you. Thank you.
Okay.
We have 8 minutes, so I don't know how we can do that justice, but we're going to try. First things, you know,
I appreciate the extra time.
Yeah, absolutely, absolutely earned it. You know, I accidentally put Terrence on the spot a minute ago and asked him for a crystal ball, and then lo and behold, you show up with a crystal ball. So thanks very much for that. That's helpful.
I think I have the base of the crystal ball,
right?
And we're still, you know, trying to build the ball.
Sure. No, it's that model that you're crafting, that simulation that you're crafting. That is a complicated beast. And I make jokes that it's a crystal ball, but it is in fact a tool for trying to understand today's actions and how they might have implications into the future. So if you were earlier speakers, Nagar with Momentous, or the Graphene Council with Terrence, or Daniel Faber with Orbit Fab, you would then take a technology, a TRL level XYZ, and put together a data sheet and then insert that into the model. Is that how that works?
That'd be one way to do it. Honestly, COVID notwithstanding, I'd like to sit down with people and kind of talk to them about their stuff and kind of walk them through it. Joel has been putting together these workshops, so I imagine a lot of these workshops will be collecting data as well.
Right.
But yeah, I think
you mentioned Joel, Dr. Mosier, Chief Scientist of U.S. Space Force.
Right. Who put you and I together?
Yeah.
So yeah, I think we could do that with just a form and whatnot. I saw us, really getting people in the room, like all the nuclear people, and let's kind of hammer out what nuclear needs to look like. When folks show up with, like the folks that you mentioned with the last mile to space and the graphene technologies and whatnot, I'd want them in the room, in some of these cases, like with graphene, that's like a component level technology that I think, we would take their inputs and integrate them with others to talk about what we expect to happen down the road.
Right.
With the folks from Momentous and whatnot, where they've actually got a piece of infrastructure that they want to build, I think that's where we could say, okay, give us, your timeline and your components, and hey, let's go run with it. I hadn't really thought until you brought it up, Michael, the idea that this could be useful to the entrepreneurial community. That at least come. Yeah, I know, and here I am describing myself as an entrepreneur with the apparatus systems and all that. So I really am an engineer first, unfortunately. But yeah, that would be a good service. I mean, you'd have to take anything that comes out of oracles with a big grain of salt. It's really there to point out things that maybe we hadn't considered, to make sure that everyone in the room has the same set of information and whatnot, and to see if there's any exploitable things. I mean, as gamers, anyone who is on here as a gamer, if you can find a grind that will really exploit the system, then we frankly want to find it before the Chinese do.
Sure.
There's no two ways about it. So
yeah, absolutely. Is there any chance that this model could become public, or versions of it? I mean, we talked about the Space Force having a classified version, but is there a way that the public can have access or build it even as a wiki tool or something? I'm
big on the idea of doing it that way. I would love to have a public version where people were grinding out their own scenarios and trying to find those exploits and whatnot. Joel has been very positive about that as well. There have been some pushes to classify some of these space futures workshops, and he's managed to resist those to some extent. So certainly the first one, you can go out and find that. When I set up the back end model, I specifically thought of both an unclassified and a classified, and probably there needs to be three, right? There needs to be a classified, a restricted data, not classified but for internal use only, and then a fully public model. And honestly, as far as I'm concerned, I'd put the whole source code out too. So, you know, it just let everybody use it. You know, there's whether or not we're allowed to do that. You gotta remember, I'm a small fish in a big pond, so I do what the bosses tell me to do.
Right.
But certainly there's that urge to have it public.
Okay, I'm gonna.
And I think there's a lot of pluses there too. I'm really big on, you know, using the group. I've forgotten the phrase now, but you know, open source development capabilities and whatnot.
Using the open source community, they are a force for good in the world. Definitely.
Yeah,
And
they're a force multiplier. You know, if you go
open
out
source
there,
folks in this call, so I'm sure they're glad to hear that.
Yeah, if you go out and say, "Hey, we need this," someone go develop it. That doesn't work. But if you are willing to put a person in to help, and you're going to get 5 people's work back in terms of, and so, you know, I think that's where we've missed in the past in using open source, is that we look at it as free work when it really is a force multiplier.
Yeah, it's an amazing source. Last question, we have really just 1 minute. I want to come back to Puff directly, and if you could have a wish list for 2022 and 2025, what does that look like?
Oh gosh,
as good as realistic, right? As big as realistic.
Yeah, as big as realistic. I would have several companies exploiting the nuclear, the medical, and the 3D printing technologies and the coil gun technologies with me, and those companies would be able to bring, you know, high 6 to low 7. Well, really, right now, low 6, but by 2025, you know, 7 figures to the table, so that I can break loose 8 figures from the government.
Right on. Okay. All right. We're going to turn it over to Katie. Dr. Adams, thank you so much for.
Thanks for having me. That was great.
Inspirational. Thank you. Thank you.
Dr. Adams, just really quick, where can people find out more about what you're doing? Where can people reach you? Do you have any websites, any asks of the audience?
Yeah, Puff has, I can type it into the message here, but it's robert.b.adams@nasa.gov. And Puff has a website. It's www.nasa.gov/Puff. And I'll type it out here right now.
Cool. Thanks a lot.
Great. Thank you.